evening. Welcome to the September novice meeting for the Houston Astronomical Society. For those of you that don't know me, my name is Chris Morisette and I'm the novice chair. So I'm happy to be here tonight. And I think I've got a really good presentation for tonight. And what that presentation is going to be is our solar system. I usually do a presentation this time of year that focuses on Saturn and Jupiter as they come into opposition. But I thought it would be fun to kind of expand our view of our home here in the solar system and talk about a lot of different planets and objects that are out there as part of our solar system. So I think this will be fun. We will also talk about Saturn and Jupiter. So if you needed some information there, don't never fear. We will still cover some of that information. So tonight, what we'll do is we'll start out with just some basic information about our solar system. And then I'll spend quite a bit of time going and using this tool from NASA called Eyes on the Solar System. And we'll do a tour. We'll go from Mercury and work our way out to Neptune. We'll look at various asteroids and dwarf planets, a comet. And then also what's really neat about this tool is you can look at various NASA space probes that are in progress or have been completed in the past. So we'll take a look at a couple of those. Once we get done with that, I'll go ahead and talk about Saturn and Jupiter, get us ready for opposition. We'll talk about filters and dates and all that good stuff that you can use in order to get some prime viewing of those planets when they come into opposition. And then we'll wrap up with some fun photos of our solar system. I've reached out and collected various photos from members of our club, members from other clubs here around Houston, and of course, I'll throw in a couple of my own. And then we'll conclude with announcements and call it an evening. So as I go through, if you would put your self on mute, and if you would type your questions in to the chat, that would be great. And then I'll come back to those when I finish up. So a little basic information about our solar system. This first graphic I found, at first I thought it was a bit cartoonish, but the more I look at it, the more I kind of like it. It shows all the planets. It shows the asteroid belt and the Kuiper belt. It shows some comets coming in from the Oort cloud. So it's really kind of a neat, cheery depiction of our solar system, and kind of grown on me. So I thought I'd include that as just kind of an opening slide here. So our solar system, let's start out and talk about where we're located in terms of our galaxy. So you can see up here, I've got our solar system circled with a nice yellow oval. And we are about 27,000 light years from the center of our galaxy. And we're about another 25,000 light years out to the edge of our galaxy. So we're in the suburbs. And as it turns out, that's a really good place to be. If you're too far in, you subject yourself to a lot of action, a lot of activity, and a lot of things that could potentially disrupt our home. If we're too far out, there may be some other ramifications there. But I think where we're located, which is on the, I think it's on the Orion Cygnus Spur, where we're located is a pretty hospitable place. Here is a picture that shows our local neighborhood, and what I've got drawn here is about a 5,000 light year radius circle with our solar system at the center. And our neighborhood is really cool. For those of us that do a lot of observing, do astrophotography, we find a lot of familiar objects located in this very short segment of our galaxy. So, for example, Pleiades, which is a very commonly wide-known open cluster, is right here. It's only about 400 or so light years away. We have the Horsehead Nebula. It's about 1,600 light years. You've got the Dumbbell Nebula, the North American Nebula. Over here, you've got the Lagoon Nebula. So you've got a lot of neat objects that are in very close proximity to our solar system. And then even going farther out, like the Eagle Nebula and the Trifid Nebula, they're not too much farther out than our the radius of our neighborhood here, which I've kind of drawn a little bit arbitrarily, but we got a lot of neat, cool things to look at here in our local galaxy or our local part of the galaxy. Another question we might have is, well, gee, how did we get here? How did our solar system get here? And I've got this simplified process to kind of outline how things happen. So, as a protostar core collapses, the surrounding construction debris flattens out, forming a protoplanetary disk. So, if you think about our Olympic figure skater, and she's in the middle of a high spin twist. She brings her arms in. You'll notice that her skirt on her costume kind of flips out, and that could be analogous to, say, our protoplanetary disk. That disk is going to be made up of metals. I've got construction debris as kind of a catch-all phrase here, but the metals, for the most part, are going to be anything really heavier than helium. And that's going to be, in our case, that's going to be what populates that protoplanetary disk. Dust will stick together, forming pebbles and rocks, which further grow into planetesimals. So you've got this motion, this spinning motion, and this material, the dust and pebbles will eventually run into each other, knock into each other, and form larger objects. As planetesimals and planets form, gravity becomes a factor, which will accrete more material. Gas from the construction debris coalesces to form gas giant planets, Jupiter, Saturn, Neptune, Uranus. Um, in addition to the metals that we have in our construction debris, we also have a fair amount of gas because, after all, that's the building blocks of our own sun. And then eventually our planets will sweep out most of the debris from their orbits and a new star will blow away the remaining gas. And that's kind of where we're at today with our solar system. Here is a depiction of our solar system going from the sun out to the Oort cloud. And you'll notice that the distance here from our sun out to the edge of the Oort cloud is about 1 light year. So that's not a very big distance at all. Our closest neighbor is Proxima Centauri, which is about 4 light years away. So we're about a quarter of the way there once we hit the Oort cloud. But when you consider objects like Pleiades and which is a relatively close star cluster, being about 400 light years away, you can see that the size of our solar system is rather inconsequential. Here, I've kind of taken that previous drawing and split it up so we can kind of look at it a little bit closer. But here we have the planets, Mercury, Venus, Earth, and Mars. In between Mars and Jupiter, we have the asteroid belt, and within this asteroid belt, we have at least one dwarf planet, being Ceres. We have Jupiter, and Jupiter contains a number of moons that you see listed or shown below the big brown spot here representing Jupiter. There are also what are called Trojan asteroids, and so you'll see Trojan asteroids are actually asteroids that follow the orbital path of a planet, and so you have Trojan asteroids that when they follow or lead the planet, they're called Trojan asteroids that are in the Greek camp. And then when you have Trojan asteroids that follow the planet, they're in the Trojan camp. So I think it would have been cooler, instead of calling them Greek, to call them Spartan, because that way it kind of gets you excited for college football, Big Ten football with USC and Michigan State, but nobody asked me. So we have Trojan and Greek camps. Just a little astronomy humor there for you. And you're on mute, so I'm assuming you're laughing hilariously. We have Saturn over here, and again, it has quite a number of moons. And one thing I do want to add is that Trojan asteroids actually are common to other planets. So um, Venus had some at one time, Saturn, I believe, had some, Mars and Earth had some for sure. I think we even still do have some that are out there. But as you do these things, you learn, and that's one of the things I learned about our universe and these asteroids. I began to become a bit of an asteroid aficionado, and I'll show you why when we get into the photo gallery. Um, Going further out here, we have Uranus and its moons, Neptune with its moons, and then we get out into the Kuiper Belt, and that's where you have dwarf planets like Pluto and some of the others. There's an odd duck that's out here called Sedna. Sedna is a kind of dwarf planet, I believe, and it is way the heck out there. It is so far out, as a matter of fact, that its orbital period around the sun's about 11,400 years. So it's way the heck out there. I think the official term for it is a Neptunian object, but that's Sedna. And then we get out into the Oort cloud. And the Oort cloud is a bit of a theoretical place, but that it's thought to be the home of many cold, icy objects, comets that come in, long period comets that come in closer to Earth and our sun are thought to have originated from this area. And so that's just kind of our solar system in a nutshell. I put together this table to just kind of lay out some basic planetary attributes. You'll notice that each of the planets are arranged in the order that they are from the sun. So we start out with Mercury and end with Neptune. I put in Ceres and Pluto as well. I can never remember if Pluto is still out or if it worked its way back into being a planet. So I included that as well. And you can see there's just a lot of very neat information here to take advantage of. I've highlighted a couple of areas that I thought were of interest, kind of some oddities, if you will. If you look at Mercury and Venus with respect to their rotational period and their orbital period, in the case of Mercury, they're just about the same. The orbital period I've got here in years, but if you do the math, it's about 86 days. So the orbital period around the sun is not much longer than its day. And you'll notice also that the axial tilt of Mercury is almost perpendicular. Venus is really an odd duck. It has a rotational period of 234 days and an orbital period of about, if you take half of 360, you're talking about maybe 160, 170, 180 days. So its orbital period around the sun is actually shorter than its day. So it'll make one rotation around the sun before it actually rotates on its axis for one day. And it has a very extreme axial tilt of 100, almost 180 degrees, hence the negative rotational period. I'm not 100% sure how they came up with that angle of rotation, but um, they sure did. And I assume it's just because of the rotation of Venus being uh, different than what the other planets are. Mars, I highlighted Mars. I didn't realize it had two moons. Um, Again, it's, planetary astronomy is not something that I really paid a lot of attention to. So like I said, as I put this presentation together and started researching it, I learned things as well, and that kind of stuck out to me. Uranus is another odd one. It has about a well, almost in this case, a 98-degree tilt. So in effect, what Uranus does is it rolls around the sun, as opposed to spin like our Earth and move around the sun. It's actually rolling like a cue ball on a pool table. So that's weird. And when we get to the tour of Uranus, we can kind of take a look at that a little bit more. There is It's not tidally locked to the sun. It will actually have, in its 84-year orbital period, half of that will be with one side facing the sun, and the other half of that orbital period, the other side will face the sun. And then finally, Pluto. I remember as a child just kind of in awe of the long orbital period of almost 248 years. It has an extreme axial tilt, similar to Uranus, and it has five moons. Charon is one of its moons, and it almost is as big as Pluto. So you almost can kind of think of them as a binary uh, dwarf system, dwarf planets. But it has five moons, and we'll take a closer look at that as well. So just a little cool information about planetary attributes of the planets in our solar system. Now we'll go to the fun part, and we'll look at this tool from NASA. I'll take us from the planets out to the edge of the solar system. We'll look at a few moons on the way, look at a few comets, asteroids, dwarf planets, and then planetary missions. And so with that, I'm going to fold that up. And then I practiced this a little bit with Heather before the meeting, and she tells me that that is visible by everybody. So if it's not, come off of mute and let me know. But I will, if I don't hear, I will assume that um, silence is concurrence. Okay? So here we are. Here is our solar system. I'll just kind of zoom out a little bit. I'm using my fingers on the screen. And there are all the planets, and we can use our cursor to kind of tilt and move around. Um, I'm going to go kind of blow that up a little bit. And I'll show you a couple of features on this tool. Uh, and I hope that you take a look at this later on because I think it's a really cool thing. It's almost kind of like a souped up planetarium. So I really enjoyed um, learning about this thing. There's a thing here called layers. And what we can do with layers is we can turn on and off things. So I'm going to turn off the spacecraft. Let's turn on asteroids. And man, it gets really busy there, so we'll leave that off. We can turn on dwarf planets, and there's Ceres right there. We'll turn that off for the time being. And there's some other adjustments that we'll use here as well. This panel right here allows us to change the lighting, and we'll make use of that. And you can use these to come in and out on a particular item. Um, there is also a little panel over here that you can kind of flip out, and we'll use that when we look at some of the space missions and maybe a couple of planets or so. But just wanted to make you aware of that. So let's start out on our journey and look at Mercury. And I'm going to do this. I'm going to change the lighting here so that we get flood lighting, and then that way I can twist and turn this thing, and we can kind of see what it looks like. But here it is. Here's a planet Mercury, and as you can tell, this planet looks a lot like our own moon, and it's not a very big planet, but it is a planet. One feature here that I did want to highlight was this crevice that you see here. It almost looks like somebody took a big crescent wrench and hit Mercury over the head with it and put a big dent in it. But what that actually is, it's called, excuse me just a second, let me get a sip of water. It's called the Great Valley, and this valley is about 600 miles long. So it runs from here up to here. Let me roll that down. So that's about 600 miles long. It's about 250 miles wide, and it's about 2 miles deep. And the creation of this valley is really interesting. So the crust of Mercury is one solid piece of material. It's not like we have here on Earth where we have plates that float along our mantle. This is actually one single crust that you see on Mercury. And what's happening is the crust of Mercury is shrinking. And when it shrinks, it pulls the crust, puts tension on the crust, and that creates this separation, and the material from the separation falls and can create these valleys as it did here. So that's a lot like if you're familiar with geology at all, there's a thing called a rift plate or a rift canyon. And a really good example of a rift canyon is over in Taos, New Mexico. The Rio Grande River headwaters are up in the southern part of Colorado. And you'll notice that Taos is out on this mesa, this flat plain, and then all of a sudden you come up to this really spectacular and deep canyon. And what's happening here is the plates, the tectonic plate motion, those plates are pulling apart, and that's what's called a rift, in that case, a rift canyon. So it's a similar effect, but again, this is a one solid crust, whereas in New Mexico we have plates that are actually moving around. So I thought that was really interesting. Mercury actually has three different axes. It has a long and a short and a polar axis. Yeah, really can't, you can kind of make out a little bit. You can sort of make out somewhat of a slight oblong shape on this planet, but it's not really clear. So the axes aren't really apparent like they would be on some of the asteroids we're going to look at. But I thought that was pretty cool. It is not tidally locked. It rotates, but it has a very slow uh, orbital rotation for its day, and it can be a very cold planet. So Mercury does not have any atmosphere, and so if we put on our natural lighting, we can see here that we've got a dark side of Mercury, and because of that what happens is you can get some extremely cold temperatures down to like minus 290 degrees. So that is really interesting stuff. So that's Mercury, and that is a very cool looking planet. And so now we're going to continue our journey, and we're going to go out to Venus. And here's Venus. And Venus is really an odd one here because you really can't see anything on the surface of Venus. Not at least not with the eye. With visually, you can't see anything. You can probably detect its terrain using radar, but you can't hear with visual technology or naked eye or so. So anyway. Let's talk a little bit about Venus. The atmosphere of Venus is extremely thick and extremely toxic. And I'm reading from my notes here, so forgive me. But it's mostly sulfuric acid, and it has a high degree of carbon dioxide. You might say that Venus is an example of runaway greenhouse gas effects. Um, Venus does not have tectonic plates like and tectonic activity like we do on Earth. So there's no way, and tectonic plate motion plays a big role in regulating CO2 in our atmosphere. So without that, you really don't have anything there to regulate the climate on Venus. So that's one thing. There are no plates. There's a lot of volcanic activity. The volcanoes here are similar in nature to what you'd have on the big island of Hawaii. Hawaii sits in the middle of the Pacific plate, but still has enough pressure from a magma chamber to create this big volcano. So you have volcanic activity, which again contributes to the thickness and the harshness of the environment there. So that's a little bit about um, Venus. Like I said, we don't have anything here other than just kind of a beautiful crescent, which will show in some of the amateur photos that I've collected from members of the club. But we don't see anything here on the surface. When we get into the photo gallery, I actually was able to find some pictures that were put together with data from a couple of Russian probes that were there. So we'll take a look at that. That's really interesting stuff. So that's Venus, a very cool planet. Cool meaning kind of neat, not cool, cool. All right, I'm going to go back with my floodlighting here. And now what we're going to do is we're going to go to Mars. And here's Mars. And so Mars is kind of reminds me of Arizona. You've got some wide open desert expanses, and then you've got some real rough terrain here in this area of Mars. And there's one feature that I do want to talk about is called Mons Olympus, and that is a huge shield volcano on Mars. And I'll kind of, with my cursor, kind of outline this here. So you've got this kind of this whole region right here, which is kind of the shoulder of the volcano, but that's all lifted up from the surface. And then here you have the cone or the top of Mons Olympus. Now, Mars is not a big planet. It's much smaller than Earth. I think it's roughly half the size of Earth. But this, and I should know that. I need to go back to the table. But it's smaller than Earth. And but this mountain, this volcano, is about 72,000 feet high from the surface, which is twice the size, almost over twice the size of Mount Everest. So it's massive. There are no plate tectonics on Mars as well, so you don't have mountain ranges being um, uh, created like you do here on Earth, but rather you have these magma chambers underneath the surface pushing up against the crust of the planet, creating these huge structures. So similar to what we talked about on Venus. Um, this width that you see here is, I think from here to here is about 300 and maybe here to here is about 370 miles. So it's a really large and impressive structure. And I've seen some amateur photographs um, that have actually captured that. So I think that's really magnificent. That's the one thing I wanted to mention. The other thing was this ice cap up here. I'm not sure if that's water or some other material. I should have looked into that a little bit closer. But that is an ice cap similar to what we have here on Earth. And again, you've just got this really rough terrain over here. I got another ice cap down there, and then you get out here into this smooth desert area over here, and you top it off with that huge shield volcano called Mons Olympus right here. So that's Mars, a very cool planet. Let's continue our journey. And now what we're going to do is we're going to go out to Jupiter. And Jupiter is right here. So Jupiter is out beyond the asteroid belt. Jupiter is a wonderful, beautiful planet. It's a gas giant. So really what you're looking at here is the atmosphere. Just to kind of talk a little bit about the features here. The dark bands that you see here are called belts. And those are areas of its atmosphere where material is falling back down or raining back down towards the center. These lighter bands that you see over here are called zones, like here and here. And these are areas that are areas where material is rising. So think of that as like evaporation of material. You have these regions at the poles here and down here that are different distinct regions of Jupiter. And let's see, what else did I want to say about Jupiter? Oh, wind speeds. Wind speeds are a really big deal here. Let's see if I can get the red spot in view here. There we go. I'm going to do that. There we go. So the winds on Jupiter are very extreme. We've got typical winds of 2 to 400 miles per hour. Um, the Great Red Spot has winds in excess of 400 miles per hour, and then at the polar regions, you have the highest wind speeds of about 900 miles an hour. So it's very extreme out there. And I'm going to try to, actually, what I was going to try to show you a transition or a shadow of a moon moving across the surface of Jupiter. But I think what I'm going to do is I'm going to save that for Saturn. because Saturn is coming into opposition here shortly, and we've seen some really cool pictures here recently. So we'll do that on Saturn. But before we leave Jupiter, let's talk about a couple of moons here. And I'm going to go over to here, and I'm going to look up. This is another way to navigate. Unfortunately, the Zoom toolbar was um, covering up where I needed to click. So I'm going to go here and I'm going to go to the planet Io. So, or not the planet, but the moon Io. So this is a Galilean moon that orbits around Jupiter. And that is really a weird looking chunk of rock. It reminds me of those cheese balls that you see at a party where, the outside's kind of rough and crumbly, and then you kind of dig in there with the with a small knife and put some on a cracker. That's what it reminds me of. I guess I'm hungry. Anyway, this is Io. And what we see on Io is a lot of volcanic activity. So you can kind of see these pock marks all around Io. Those are volcanic vents. Uh, uh, I'm surmising that those are volcanic vents. Now, you may ask yourself, well, gee, how does volcanic activity, which we think of as a hot, and it certainly is as a hot um, um, phenomena. How does that happen so far out from our sun? Well, in the case of Io, it is a relatively small object that is orbiting a massive object. And of course, its orbit is not perfectly circular. So there's going to be some points at which the gravity changes, and you're going to get a lot of twisting and strain and stress on Io itself. And it's thought that that heat generated from that stressing and straining of the moon is what causes this volcanic activity. As a matter of fact, several volcanoes on Io produce plumes of sulfur and sulfur dioxide that can climb as high as 300 miles. So very active moon, and it's the closest one into Jupiter, or certainly of the four Galilean moons. So that's a little bit about Io. Let's go look at Europa, because I know tomorrow night there is a presentation on the Europa Clipper, and I hope you all can attend that because that ought to be really interesting. And we're going to go down a little bit farther. Yeah. So let's take a look at the moon Europa. And Europa is really kind of radically different than Io. Here, what we have, what appears to be a coating of ice or some kind of frozen material on its surface, and there is believed to be a large ocean underneath this surface. And as the Moon will orbit Jupiter in similar nature to Io. You could imagine where you would get stressing and straining on that crust, material coming up from that ocean, resurfacing the surface of Europa, as well as some cryogenic volcanic activity. That's why you see such a smooth surface, or at least that's the hypothesis here. And we'll learn more as the Europa Clipper gets out there. But that's Europa. There's a good chance that perhaps we'll find life on Europa inside the oceans. I'm not sure to the extent to which they're going to examine Europa. So I've got to tune in tomorrow night and find out more about the Europa Clipper. Now it's on its way out there, and we'll look at the Europa Clipper here when we get into some of the NASA programs that are depicted in this model. Okay, so that is Jupiter and a couple of its more distinguished moons, Io and Europa. And now we'll kind of zoom back out here and we'll make our next stop here at Saturn. And I got to tell you, I think besides Earth, Saturn's one of my favorites. So I'm going to do this. Now, I'm going to try to see if we can spot a shadow of one of the moons going across the surface. So we'll give this a try and see if we have any luck. Um, Sometimes this worked great for me, other times not so much. But if we can, let's see if one of these moons circling around Saturn, if we can catch um, the shadow transiting the surface of Saturn. Let's see. Give it just, we'll try it. We'll try it for a little bit. I don't want to spend too much time on this, but I thought it would be kind of neat to catch it in the act if we could. And let's see. Yeah, I'm not seeing it. We may not be at the right angle. Let's do this. Let me try changing the lighting, and I'll go to natural lighting, and let's see if we can't do this. We'll kind of get in front of it where it's pointing towards the sun, and we'll see if we can catch it. Mm. Oh, there it is. So there's a shadow transit right here. My guess is it's coming from uh, and I'm not sure I'm pronouncing this moon's right, but it's in Enceladus, and I'll bet that's what it is. We'll just slow down this rotation a little bit and see if that might be the moon. But anyway, so we did see one, so that's kind of cool. So this is Saturn, and I just wanted to show you that because, again, it's coming up in opposition, and we'll be able to see some really cool images of that. Hopefully, some more transitions. I've got the natural lighting on, and some of the pictures that we've seen back from um, Cassini showed us this really gorgeous looking shadow that's cast from Saturn onto the rings, making even making a section of them appear to disappear. So I thought that was really cool. Um, let's go back to our flood lighting and just kind of talk a little bit about the rings, its most distinctive feature here. Now, these rings are about 175,000 miles end to end. So from here all the way up to here is about 175,000 miles. So the distance from Earth to the moon is about a quarter of a million. So it's darn near that distance from end to end on these rings. The thickness of these rings averages about 3,200 feet, and I think there's some portions of these rings that are even thinner than that. So they're made up of ice and rocky material, and these divisions are these separations are made by moons that are actually small moons that are actually orbiting around inside of the rings. So really an amazing structure here. Now there's a couple of moons here that I wanted to focus in on because Saturn has a couple of really unreal looking moons. So this first one here is Mimas. And Mimas has this giant crater that is huge in relation to the remaining surface of this moon. And of course, the idea here is that that was created by some gigantic impact that may have at some time almost split the thing in two. It's just a huge crater. And that's Mimas. I didn't really have much more to say on Mimas. Didn't want to shortcut Mimas, but I'm going to go back out and we're going to look at another moon um, called Iaptis. I hope I'm saying that right. And let me go down here and find that. There it is. And this one's really, really a weird looking one. You notice this nice chalk-like surface, and then as we rotate it, you see what looks like just charcoal. So some object has come in here and just careened into this moon and created this splash, if you will, of almost kind of looks like mud. So it's really, really amazing. So that is Iaptis. And the last moon I wanted to look at was Enceladus, or let me see which one that is. Bear with me just a second. I think it was down here. I think it was the one we saw where the shadow was coming across. And so let's look at this one here. And the cool thing about this moon right here is you have these, and I went to the wrong menu here. Let me change the lighting, and we'll change it to the natural lighting. And here's the thing I wanted to point out of uh, these spouts of cryogenic volcanism on this moon. And you can see these jets coming out from the moon, and it's really an amazing feature. So those are the moons of Saturn and Saturn itself. And now let's continue our journey out, and we will go to Uranus. Now, Uranus is kind of a weird one here, and we'll take a look why. So the thing about Uranus is pretty cool, and I'll keep that flood lighting or that natural lighting on for right now. But the thing about Uranus, it's pretty neat. It does have rings. Um, there are 13 faint rings actually, and you kind of see them here. And then you also have this tilt that we talked about earlier, this axial tilt. And you kind of see, sort of see the manifestation of that with the shadow that's along the surface of Uranus. And again, this planet rolls like a ball across like a pool table. And again, it's not going to be a situation where the where one side gets sun all the time, but rather one side will get sun half of the time, and the other side will get sun the other half. So that's Uranus. It's got the nice rings out here. It was discovered by William Herschel back in 1781, and it was really the first planet that was discovered since antiquity. So that was really a neat finding by Herschel um, back in the day. Now we'll continue on our journey here. Let's go to Neptune. And again, I'm going to have to kind of close everything, kind of zoom out a little bit. And here's Neptune. And Neptune also has rings. Let's see if we can detect those. They're really faint rings at Neptune. This is the only, there we go. This is the only planet that is not visible to the naked eye. So we do need telescopes or some other device in order to see this. But this is Neptune. It is the densest of the gas giants, and it is next after our Earth. It's the next in line next largest planet, but it's much larger than our planet. So that's Neptune. Um, so now let's go out to Pluto. And for here, um, we're gonna go we're gonna go out to Pluto, and I'm gonna have to turn on the planet, the dwarf planet layer. And here's Pluto. So let's go out and take a look at that guy. And Pluto, I'm going to turn on the flood lighting so we can see it. And there's a heart-shaped uh, area of Pluto that you see right in here. And this is thought to have been a impact of some sort um, from long ago. And what you see down here on the bottom of this crater or valley is frozen nitrogen. And so that's what you see down here. Um, there is not a whole heck of a else to speak of here. I'm going to try and find Pluto's moon Charon. Let me see if I can just spot it here in its orbit somewhere. I thought that was it. Let me see what this thing is. And let's see if that's Charon. And there it is. And this is that little info panel I was telling you about. You can pull this thing out and you can get some more information on the planet. All right, so that's Charon. Again, I just wanted to show you that and show you what it looked like in relation to Pluto, and they're practically the same size. Okay, so those are our dwarf planets. Let's continue on with our journey here, and we'll go look at some asteroids. So let me go here, and I'm going to go look at Bennu. And Bennu is an asteroid in our asteroid belt, and it is one that we went and retrieved samples of here back in 2023. This asteroid's about 1,600 feet in diameter, kind of looks diamond shaped here, and it's amazing to think that we were able to land something on that and bring samples back. So that's Bennu. We'll go to one of my favorites is called Psyche. And here's Psyche. And this is the weirdest looking thing I've ever seen. Look at that. You've got this really weird looking crater here. And this is, they're actually sending a mission out here. This mission is actually geared towards looking at Psyche because it's believed that this is an exposed core from a protoplanet. So it's an iron core. They think by going and examining this, they can learn a lot about planetary formation. So that's why Psyche is of interest. And that's Psyche. I'll quickly do a comet, and we'll do Halley's Comet. That's kind of a famous comet. Now, this comet right now is way the heck out from its orbit around our sun. What I'm going to do, I'm going to turn on the comet um, thing. We'll turn off the dwarf. And what we see here is this comet, but it is let's see if we go out here, maybe we can get a better view of it. And there's its orbit. And so if I crunch this in, you can see Halley out here. It's beginning to make its turn back towards Earth, but it won't be here for another 47 years. But that's Halley's Comet. And you can see right now it just looks like another asteroid. No tail, unfortunately. I tried to find a comet that did have a tail, but I wasn't able to find one. Okay, now let's take a look at just a couple of space missions. So bear with me. I just want to show you this functionality here. But this is the space probe that's going to go to Psyche. And the neat thing about this tool is you can actually come in here and see the probe. You can pull out this panel, learn about it. And what we can do here on the timeline is we can actually go to the asteroid. So there it is in and around Psyche. And again, it's going to be examining Psyche because it's believed to have been an exposed protoplanet iron core. So that's that. And then the last one I want to show you is the Europa Clipper, because that is one that we'll be hearing about tomorrow night. So let's just take a quick look. And then we're almost done here, folks. I'm looking at the time. I think I still got time, so we should be okay. Let's see, Europa Clipper, there it is. And there it is. And there's the Clipper. There's the spacecraft. Again, if we pull this window out, we can see that there's going to be an Earth flyby, I think, to kind of sling it out to Jupiter. And then in 2030, we'll be in Jupiter insertion orbit. And so you can do that with the timeline, kind of move it ahead in its mission. So that is our tour using this tool. I think it's really cool, and I hope y'all have a chance to play around with it. The website for the tool is there on the slide. So it's just solarsystem.nasa.gov, and I thought it was pretty neat. Okay, now let's talk about Jupiter and Saturn in opposition. So Jupiter comes up in opposition this coming January, January 10th to be exact, but Saturn's going to be in opposition here at the end of the month. And here's where you can find it. This is our Sky Maps map, and you'll notice I've got this area of the map highlighted here to show you where you would find Saturn in the night sky. Here's opposition. So opposition is when a planet like Jupiter and Saturn is in its orbit around the Earth, and it'll be at its highest point at midnight, and as a result, it'll be at its we'll be looking through the least amount of atmosphere at midnight. During the dusk and dawn is when you'll see it on the horizon, but when it's nice and dark, you'll have an optimum view of the planet. This is retrograde motion, and again, this is to give you an idea of what happens when we are in this track meet with the other outer planets. We are in the inner lane, so to speak, and as we move past those outer planets, they appear to circle back on themselves. So that's just a little bit about retrograde motion. And this is showing Mars, but we get the same phenomena with Jupiter and Saturn as well. Here's a nice pictorial that kind of shows you the different size telescopes and how they would compare to the view of, in this case, Jupiter that you get through an 18-inch telescope. So this kind of helps you understand what can you expect to see when you have various sizes of telescopes. So we go from 3, 4, 6, 8, 11, and 14 inches, and it just kind of gives you a comparison. Another great tool is to use astronomytools.com. There you can plug in all the parameters of your telescope and eyepiece or your telescope and camera, and you get a nice field of view for what your system will produce. So that's another way to do it. Um, Remember that magnification is going to depend on your telescope aperture and also on your seeing conditions. So you may have a small aperture telescope, say a 4 or 6 inch telescope, and with a common eyepiece, something in the neighborhood of 25, 30 millimeters, you may see a small but crisp view of Saturn. As you put in a larger or a shorter focal length eyepiece, that will begin to make things look fuzzier and fuzzier. And it's because you're spreading that light over a wider surface area. This is the same thing that you'll see if seeing conditions are poor. So just be aware of that. What is good seeing? So when a planet is high in the sky, one looks through 40 times as much atmosphere on the horizon as in overhead. So at opposition, the planet is at its highest around midnight. During a temperature inversion, when warm air overlays cooler air, the atmosphere is stable and there is very little exchange of air vertically. And so you don't have any turbulence, and these warm, hazy Houston nights are fabulous for planetary observing. So for Saturn, definitely can expect that unless we get a cold front through here, which I hope we do. I'm getting kind of tired of the heat, but we'll probably still have some warm, humid weather. So we'll hopefully that'll give us some nice viewing conditions. And then when we get into Jupiter, in particular in January, you want to avoid looking at the planet after a cold front because you'll have a lot of turbulence and that'll tend to ruin your seeing. Here is a chart that shows you um, different filters that you can use to help enhance various features of these planets. So we had a presentation by Draco back in May or June rather, and he covered uh, a lot of information about filters. This table can kind of give you a good picture of what you need to use if you want to look at the Cassini divisions or the belts on Jupiter, so on and so on. And this is at Agena Astro. Here is a chart that kind of shows you what we can expect to see with Saturn. Unfortunately, this year it's going to look edge on, so it won't have those beautiful broad rings like we've seen in years past, but still really cool to look at. Okay, so that was just a little bit about opposition. Let's run through some fun photos. And this first one is not a photo, but rather a gift that I got from Sonny Manley of the Sun. Sonny is in our club, and he had taken this beautiful image, almost hypnotic uh, set of images from the sun. You can see the prominences coming up off the surface. You can see some sunspots over here and all this kind of boiling and churning on the surface of the sun. It's really impressive. To give you some scale, our Earth would probably fit in this region right here. So these are massive. So that's our sun. When I was putting this together, I realized it didn't have anything on Mercury. So I went out on the morning of August 18th, and I was lucky enough to capture Mercury, Venus, Jupiter, and the Moon in a row here on the ecliptic. Now, the view of Mercury was really tough to see here because I was fighting that morning sunrise. So I blew that up to show, yes, indeed, I did see Mercury there. But here's another picture of Mercury on that same morning. Uh, One thing I just want to point out here, this I did this with an iPhone, and we see these beautiful images of planets and nebula and etc. But you can still do a lot of really neat things with the iPhone. Artistically, maybe it's not the most elegant, but it is a great teaching tool. So I just wanted to make that point. After I put this together, I remembered that a friend of mine had actually captured the transit of Mercury back in 2016, so I included that as well. Um, he used an iPhone through the eyepiece of his 16-inch Dob. So here again, um, nothing that is really fancy or artistically pure or crisp, but still serves a nice educational purpose. Here's a comet, Shushan Atlas that I took back last October. Here you can see it in its position. The night I shot it was between Venus and Mercury. Very nice comet. Was glad I was able to capture the bright core and the nice tail. Um, so that was really neat. Here is Venus. I got this from Bob Rummels. He's in the club, and he did a wonderful job on capturing Venus. Here again, the image is all cloudy, like we saw in the tour. But here's a picture I got off of the web from a couple of Russian missions back, I think, in the early 80s. And this lander, I don't think it operated for more than an hour, but this is the landscape that it was able to photograph. And this guy by the name of Don Mitchell had gone back and reprocessed these to kind of show us what we had. They kind of look like some of those early pictures from Mars, but you can tell that the atmosphere is just very bleak. But that kind of gives you an idea what the surface of Venus looks like. Here's our moon, and you can see some nice uh, debris streaks coming off from the impact that created Tycho. Uh, they kind of extend out here and almost halfway around the diameter of the moon. And you can see the crater Plato up here and all kinds of other features. So that's our moon. Here's Mars from our own Andres Salaveria. You kind of pick out those mountainous regions bordering up against the kind of the flat desert areas here. And that's a very nice picture indeed. Next is an asteroid. This is a special one. For those of you who may or may not know Tracy Canas, she is, I believe she's the manager of the George Observatory. I'm not 100% sure on her title. But anyway, an asteroid was recently named after Tracy. And here it is. It actually shows up in Sky Safari now with her name. And it is out in the asteroid belt, and it orbits the sun once every 8 years. This was discovered by some people in FBAC. They were actually doing some studies of this comet, and in the process discovered this comet or this asteroid, and they submitted it to the proper authorities and were granted the they were able to name it after Tracy. So I thought that was really neat. Somebody, I actually know somebody that has an asteroid named after, so I thought that was really cool. Moving along, we have Jupiter, another entry from Sunny Manley. Very pretty. See the big red spot in the bands here. Wonderful image. Saturn by our own, again, Andres Salaveria, and he captured it at a time when the bands were very visible here. Here's a panel that I got from a guy by the name of Todd Dunavant. I like using this because number one, it's the only picture of Uranus and Neptune that I have. And second, he did a really nice job kind of putting this all together. So that's our entries for Uranus and Neptune. And then finally here's a couple of conjunctions. I captured this one back in 2020 when we had the great conjunction between Saturn and Jupiter. They were very close together. And then the other morning, I captured Venus and Jupiter at about a degree and a half separation. And as an added bonus, I got Orion over here in the early morning sky. And so that was nice because Orion says winter's coming and things are going to cool off. So with that, the presentation is concluded. I'm going to go ahead and just dive into the announcements. We have our special interest group meetings in September. We have the visual SIG on the 10th, the smart telescope SIG on the 17th, and astrophotography on the 24th. There's a note that came out from Stephen, but you can also get the details for joining the meetings on the web. Renee just put those on there. And then tomorrow night we have at 7 o'clock our general meeting that will cover the Europa Clipper, and that will be given by Dr. Walter Kiefer. So with that, I thank you, and I'm going to stop sharing and go ahead and look at what we've got in our chat. So Darcy Baldwin asked, isn't water ice plus CO2? I think water is H2O. So I don't think there's any, there may be some CO2 that's maybe captured in some of the ice, but um, if my memory serves me right, it's CO2 or it's H2O. Oh, the ice cap on Mars. Oh, isn't it water plus CO2? Okay, yes, you may be correct. And again, I could kick myself for not researching that more clearly, so forgive me on that. Does anybody know for sure on those caps that are on Mars what they're made of? I can just come off mute if you'd like.
There is certainly both water and CO2 in the Martian ice caps.
Gotcha. Thank you, Bill. Okay, Bill, the favorite hypothesis for the dark side of Iaptis is that debris from Phoebe or other unknown outer satellites of Saturn impacts the dark hemisphere of Iaptis on. Bill, can you come off mute and talk? Why don't you come off mute a little bit and talk a little bit about that?
Okay, first of all, this is not Bill Spizzeri saying this. This is from the NASA website. And so they're saying, you know, Iapetus, one side is very bright, one side is very dark, and they're trying to say that impacts on Phoebe, which is another moon of Saturn, and some other unknown satellites of Saturn, the debris from those impacts are what's hitting Iapetus and darkening the dark side.
I gotcha.
If I interpret that, the wording is a little strange, but that's how I interpret it.
Okay. Yeah, that makes sense. I was a little vague on that. Something was impacting it and causing it to get that charcoal look. But
Well,
yeah,
don't feel bad because NASA was vague on it in their own website.
oh, okay. All right. Well, good. Well, thank you, Bill. Appreciate that. Cora asks, what is the name of the tool you are using? So that one's called um, Eyes on the Solar System. And if you go to that website that I had, which was, well, what was it? Let me,
I got that, Chris. Thank you. So,
did you?
yeah,
Okay.
yeah, thank you very much. Appreciate it.
Okay. You bet. All right. And then, yes, so thank you, Chris, for the compliment. I appreciate it. And with that, if anybody else has got any questions, feel free to just come off of mute and fire away. And I'm gonna go one. Oh, Heather.
That was a great talk. I really like that app thing. That's pretty cool.
It is very cool and something that you can use when Saturn and Jupiter come up here in opposition. You can use it to kind of get a more refined view of the transiting of the moons and things like that. So hopefully that'll help you out.
I'll probably also be on it during like work meetings when I'm working on Zoom.
Yeah.
Hey, Chris, you said that Saturn was September 21st.
Yeah, September 21st is
What's
when
the date for Jupiter?
It's January 10th, 2026.
Thank you.
You bet. Okay, great. Well, listen, I'm going to do my auctioneer imitation, and if anybody's got any other questions or comments, I'm going to go once, go twice, sold. So with that, I'll call an end to the meeting. I thank you all for joining tonight. Really enjoyed it, and I hope you have a chance to get out there and see Saturn tonight and when it hits opposition. So have a great evening, everyone.